I welcome you all on this course on modeling and simulation of dynamic systems. In this lecture, we will be seeing, we will be continuing the bond graph elements of my previous lecture, and after we complete the description of these bond graph elements, then we will look at the concept of causality, which is a very powerful tool in bond graph modeling and which helps us in deriving the system equation of any dynamic system in an algorithmic manner. So, apart from the three elements which we have seen in our previous slide, that is energy storage elements I and C and a dissipative element R. This in this lecture we will be looking at the two other important elements, that is the gyrator and the transformer. The transformer element, as I said, it is a two port element and it is represented like this, that is there is a power bond, then we have the TF element and there is another power bond. Here a arrow basically represents the direction in which the flow relationship is going to be implemented, and mu represents the modulus of transformer. So, these are the two port elements altering magnitude of either flow or effort, fine, and these relates flow to flow or effort to effort with the help of this transformer modulus which I just discussed to you. Fine. Then we can take many examples of the transformer elements such as say gear set, pulleys, or the electric transformer itself, okay, or the lever, fine. So, this figure actually shows you the schematic of the electrical transformer. The input side voltage is say U1 and output side voltage is U2. So, this is how it is represented, that is this is the input side and this one is the output side, and the transformer modulus is here represented as 1 by m. Likewise, here say a piston cylinder arrangement, here in the piston side we have the pressure P and say volume flow rate at V dot, and at the other side we have the force acting on the piston as F and the velocity x dot. Then this scenario can be modeled using a transformer element, and here at the left hand side we have the pressure P and the volume flow rate V dot, and the right hand side we have the force F and velocity x dot, and of course, these are related through the transformer modulus 1 by A. So, you see as I said the velocity relationship, it is being from say input side to this output side, x dot will be V dot divided by A, that is what it is going to be, or if you look at the other side, the effort relationship will be reverse, that is P will be F divided by A. Likewise, we can define the transformer modulus for a lever. Okay. So, here the input size in the input side the effort variable is F1 and flow variable is x1 dot, and at the output side say effort variable is F2 and the flow variable is x2 dot, and by this seeing this figure we can find out the modulus is P by A. So, this B by A will be modulating the velocity or the effort. Next, another very important bond graph element is gyrator, which is represented here like this. So, you have side here say input side and output side. So, here you have bond say 1 and bond 2, again as I said these are the two port elements because they interact through rest of the system through two sides, and say the modulus of the gyrator is represented by R. These two port elements relate input effort F2 output flow or vice versa through a modulus. There are examples like motor and generator or the gyroscope itself which can be modeled using the gyrator element. Let us take an example. Say this is a simple example of the gyroscope. Here suppose there is a disc which is attached to a shaft and it is spinning about a pivot here by say omega 1 angular velocity omega 1, and suppose in this case if I apply a force say in F2 direction, it will start moving in the V1 direction. This is what is the gyroscope principle is, okay, and this F2 will be given by the gyrator modulus R into V1. Okay. Likewise, if we apply a force in F1 direction, it will be start moving in the V2 direction, and this F1 will be R times V2. Let us take another example of say motor, which is again a 2 port element. Okay. So, here in case of motor, suppose we supply a voltage E across the terminals of the motor and say the current through armature is I, and say other side that is the mechanical side, we have the torque T and angular speed of the rotor as omega, then you know that the torque generated by the motor is proportional to the current, okay, and so this torque is equal to I cross a constant which is gyrator modulus in this case, or the motor torque constant for the motor. Okay. Likewise, we can write it for the reverse case, that is the voltage generated across the say when it is acting as a generator, the voltage generated will be equal to R into the angular speed, that is the speed at which the shaft rotates. Now, the zero junction elements we have been talking about. The zero junction elements are basically the constant effort junction. So, in case of the zero junction, suppose this is the scenario, that is the flow of liquid through pipes. Here say F1 flow is coming from here, F2 coming from here, and say F3 is going, then we know that in this example the pressure is going to be same everywhere in all the 3 sides. So, we write P1 is equal to P2 is equal to P3, and in this case your F1 plus F2 is going to be equal to F3. So, this scenario represents a zero junction structure, which is nothing but the constant effort junction, and here the efforts are the pressures. Okay. So, in case of zero junction, your efforts are equal, whereas the flows are summed up as per their direction. Likewise, we can have a look at this simple electrical circuit, a parallel circuit. Now, here you see that the current I1 is getting bifurcated into I2 and I3. So, here basically I1 is equal to I2 plus I3, and voltages are going to be the same across the source and these two capacitors. So, E1 is equal to E2 is equal to E3, and here you have the summation of the flows. So, this is how the zero junction element can be represented. There are many examples of zero junction. Here say as I said, the zero junction we also know it by the name of the constant effort junction. Okay. So, suppose if you have a scenario like this, that is there are 2 carts which are moving with velocity say x1 dot and x2 dot. Okay. Then and they are connected by a spring say, then naturally this spring will be subjected to the constant force. Okay. So, here the bond here, one bond here is the bond say for the velocity of the first cart, say x1 dot, here you have the velocity of the second cart x2 dot, and in between we have a spring. So, they are going to be connected through 0 junction, because the effort is going to be same through all these 3 elements. Okay. Or otherwise I can say that this spring will be always subjected to the velocity difference of the 2 carts. Okay. So, from here we can see the x3 dot is equal to x1 dot minus x2 dot. Similarly, I can explain you a scenario of say a parallel circuit of consisting of capacitor and a resistor. Okay. So, the voltages are same across all the capacitor and resistor here, and of course, say it is a current source. So, current source here. Fine. Likewise, we can a hydraulic system we can represent here that say this a pump filling a tank, and there is a flow from the discharge from the tanks, the 2 discharge. So, in this case again your pressure is going to be the same across all the elements. Okay. So, this scenario can be again represented by the 0 junction. Next, take the example of one junction element. Now, one junction, as I explained to you, is a constant flow junction. Okay. So, in case of say RLC circuit, we know that the flows are going to be current is going to be the same across all the elements. So, this type of situation, constant flow situation can be modeled using one junction, and of course, when currents or flows are same, we are going to have the summation of the voltages across all the elements. Likewise, if you take an example of the mechanical system, say there are 2 blocks which are connected by a spring, then suppose suppose if I am trying to see this block. Now, this block here, the block and the spring here, they are going to have the same velocity, but the forces of course will be subjected to the resolution of the forces in say in the direction of motion of the block and in the perpendicular direction of the motion of the block, and that summation will be decided by the Newton's law. Here are again various example of one junction. Here say there is a cart and it is connected through springs and a damper, and the other end of the spring and damper is rigidly fixed say to the inertial system here. Now, here we see that the spring, damper and the mass all are going to have the same velocity here. So, this is what we can model as a one junction, and then we can represent the force and say the spring and the mass and the damper. Okay. And here say in case of series circuit, again as I said, the current is going to be same through all the elements. So, here we are going to have a one junction, or here say a flow through pipe, here flow is going to be the same across all the sections. Here say there are 2 restrictions, constrictions R1 and R2, but we are going to have the same flow. So, we put the one junction as the constant. Now, let us look at the constitutive laws of the junction elements. Okay. So, as I have been talking to you that in one junction we are going to have the same flows through all the elements. So, naturally the efforts are going to be summed up, and how they are going to be summed up, that depends on in what direction those power bonds are. So, suppose in this figure we have various elements, say element here which are interaction of these elements is represented through say bond 1, 2, 3, 4, and say all the power direction of the bonds are towards the one junction here. So, we can simply say that the power across all the bonds is summation of the power is going to be 0, and one junction being a flow equalizing junction, I can equate the flows, and if I substitute this in this equation, we will be having a equation consisting of the summation of the efforts. Okay. The same concept we can apply to this scenario, where of course the power direction of say 2 of the bonds is reverse as of this one. Okay. So, here again I can write the conservation of power equation here, say power power in if I take as positive. So, E1 F1, E2 F2 is going out, so minus, E3 F3 again going in, so plus, and E4 F4 going out, so minus. So, this is 0 and I put the flow condition F1 all the flows to be 0 equal, and so if you substitute this, then we get the effort relationship. So, this is what is about one junction. Okay. Next about zero junction, say the scenario is like this, that the constraint among these 4 elements is represented by a zero junction. So, again I can write the power conservation equation here, and here zero junction being the effort equalizing junction. I can substitute the equality of the efforts, and if I put these values here, then I get the summation of the flows here. So, in case of zero junction, we have efforts are equal and flows are summed up, and the summation depends on or the sign of summation here depends on how the power directions are there in these different bonds. Again, let us take another example, and here we can see that the two bonds, in two bonds the power is in, whereas in other two bonds the power is out. So, again if we do the same process, this is what relationship we are going to get. So, this is all about the zero junction. Another very important concept in bond graph modeling is the concept of causality, which is nothing but the cause and effect relationship. Okay. So, let us look at what do I mean by cause and effect relationship. If we look at the Newton's law, it says that F is equal to m into A, that is force is equal to mass into acceleration, or here if we say that acceleration is equal to force divided by mass. Now, is this a causal equation? No. Why this is not a causal equation? Because here we do not know what is the cause and what is the consequence. So, if I write this equation into say this form, okay, that is momentum is equal to integral of the effort, alright, or from limit with minus infinity to t, or I can write it from 0 to t plus certain initial value. Now, in this case we can say that the effort is being integrated and a momentum is being generated. Okay. So, effort is the cause and the momentum is the consequence. So, this type of equation is what is called as the causal equation. Okay. Or I can write it in terms of our power variables of the bond graph, that is the effort and flow. So, I can write flow as 1 by m into integration of effort. So, this equation is what is the called as the causal equation. So, here effort on a mass causes flow, and this is an integral form of equation. Now, these causalities establishes cause and effect relationship between the factors of power of a bond. The history of cause signal must decide the present value of the consequence signal. This also indicates who causes what to whom. Okay. So, in the bond graph modeling, to represent the causality, what is done, the information of effort is represented by putting a small transverse stroke or causal strokes at the end of the bond graph. So, the open end is the end open end where there is no stroke, it means that that end is imparting the information of the flow to the interacting junction or the element. So, here this is say the some here some element or junction A, and here say some element or junction B here, and say this is the our power direction. So, as I said, the power direction means it is a fixing of a coordinate system, okay, in the bond graph modeling. Now, here effort and flow, they represent the power variables, fine, and here stroke here basically means that the effort information is being known for A here, okay, and here there is no stroke, it means that the flow information is being known for B. Okay. So, here the causality means E is input to A and F is output from A, or here I can say that the F is input to B or E is output from B. Okay. So, we can have the same thing is being explained here by another way. Now, here you can see that say some element or junction A and here some element or junction B is there, and if we put a stroke here means E is known for A and no stroke here, it means that F is known for B. We can have the another situation like this, that is a stroke is put being near the B. This means that the E is known for B and F is known for A. So, with this concept we can go for the bond graph modeling causality of the bond graph element. So, sources, you know that the sources, a source of effort will always be imparting effort to a junction. Okay. So, here you will have the stroke and here there will not be stroke. Then we have the source of flow. Source of flow will always be imparting flow to the junction. Okay. So, here there will not be stroke. So, here you are going to have the stroke. And for R element, you see the relationship from Ohm's law is V is equal to IR, or I can write it I is equal to V by R. So, for the R element causality could be either way, that is here it receives flow and it returns effort as per this law, or it could be otherwise here that it receives effort and it returns flow as per this law. If we look at the causality of the storage elements, say I element, so for I element this is going to be the equation which we can derive from the Newton's law in the integral form. So, in this equation we see that the effort is being integrated and flow is being given. Okay. So, the I element will always be receiving effort and it will be returning the flow. So, in this case the causal stroke will be here. Similarly, if this integral causality is not there, then the other form of causality, that is I receiving flow and returning effort, is what we call it as the derivative causality, and for derivative causality this is going to be the equation which is going to be applicable. Okay. And since all the numerical algorithms are integrating in nature, we prefer the integral causality so that we are able to simulate our systems. Okay. Next, let us see the causality of storage C element. Now, for the C element in the integral causality is like this, that is they receive flow and they return the effort. Why? Because for the C element this is going to be the expression which is being applicable, that is the flow being integrated, and if it is being multiplied with some constant it is going to return the effort. So, C elements receive flow and it returns the effort. Likewise, if we have the causality otherwise, that is C receiving effort and returning flow, we call that type of causality as derivative causality, and the equation which is applicable here is this one, and as I said we are always interested in integral form of causality. So, storage elements are said to have desirable causality if it is integrating, and numerical routines are designed to integrate and not differentiate. That is why we prefer the integral causality, and inertia are always effort causal because they take effort and return flow, whereas the compliances are flow causal because they take flow and they return effort. Causality of junctions. Now, if I talk about one junction, then for a one junction is a constant flow junction. So, the flow has to be decided by any one of the bonds which is part of that junction. Okay. So, the flow information should come from any one of the bonds and rest of the bonds should have the effort information. So, in case of this is how the causal structure is going to be. So, here this bond will be bringing the flow information and rest will be having the effort information, and this bond which brings in the flow information, what we call it as the strong bond. Okay. So, likewise so for this one junction as strong relationship we can write, as we have seen in the previous slides, the equalities of flows, and the weak relationship be the one that is the relationship among the efforts, and which comes out from the conservation of power principle. Then let us look at the causality of zero junction. The zero junction is again a constant effort junction. So, the effort information should come from any one of the bonds and the all other bonds should have the flow information. So, in that case this is what the causality is going to be. So, this bond brings the effort information and rest bonds have the flow information, and this bond we call it as the strong bond. So, again the relationship, the strong relationship will be the equality of the effort, and the weak relationship will be relationship among the flow variables, which will be coming from the conservation of power equation. Then let us look at the causality of the two port TF and GY elements. So, for two port elements, since they manipulate either flow or effort, so they will be bringing effort in and they will be sending they will be bringing the flow in and the flow will be out. Okay. So, the relationship here will be F2 is equal to mu times of F1. Okay. So, since flow information is here, the effort information has to be here, and since flow information is here, the effort information has to be here. Okay. And the transformer element can have the other type of causal structure as well, that is they bring in effort and then they give out the effort, and in this case this is going to be the relationship which is which will be applicable. Next let us see the causality of the two port GY element. Now, GY element, as I said, it is a gyrator element, it manipulates effort and flows both. Okay. So, here in this case the applicable relationship E2 is mu times of that of F1. So, in this case they bring in flow and they return the effort. Okay. Or yes. So, this is what is going to be the relationship in this case, and if they have the causality otherwise, then here you can see that they bring in effort and they return the flow. So, in this case this is going to be the relationship which will be applicable. Now, how this causal assignment is to be done in an actual bond graph model, so that there is no confusion, okay, and there is no errors inconsistency in the system modeling. So, there is a certain procedure which need to be followed, that is first of all we causal all the sources, okay, and then extend this causality to the junction elements 0, 1 and the two port elements TF and GY. After causaling sources, we go for the causaling of the integrally causal C and I elements, and again extend the causality to 0, 1 TF and GY. Okay. And after this R element is causal, and the causality of the R element is given in such a way that your whole system model is integrally causal. So, this is what is done. Okay. Now, through causaling here we can analyze our model, as we know that the causal analysis shows the dependencies, and we can derive the state equations directly from the causal bond graph model, that in fact we will be looking at in one full half an hour lecture on the derivation of the system equations. We can derive the signal flow diagram and transfer functions using the Mason's rule and the bond graph, and yes, and we can do the controllability as well as observability analysis from here. Now, what is wrong with differential causality? I have been talking to you about integral and differential causality. So, let us see what is wrong in the modeling process if you get somewhere the differential causality. Let us take an example of charging of a cell by charging of a cell by a say voltage source. Okay. Here say we have a source voltage source and here a say capacitor. Okay. So, I can model it using this way or this way, sorry, this is charging of a capacitor, fine. So, I can model it either this way or that way. Now, let us see what is happening to the causality. So, the causal is here stroke, and in this case C element the causal stroke is here. Now, we see that these are differentially causal thing. Okay. Now, let us look at what is the energy given by the cell. So, the cell gives an energy of Q by Q square by C, alright, and what is the energy stored? If you look at this derivation, the energy stored by the capacitor is Q square by 2C. So, energy given is Q square by C and energy stored is Q square by 2C. So, where the half energy has been gone? Basically it has been dissipated. Okay. So, we need to model the dissipation here also, okay. Then we can get rid of this differential causality. So, the bond graph model has to be like this. So, one R element being shown here to show the dissipation. So, this is the correct bond graph. Okay. So, neglecting resistance from the model is wrong. And what do we mean by system with differential causality? Okay. In system modeling, these differential causality usually occurs in systems having such storage element of which the output are determined by the output of the other storage elements or the sources. Okay. And in such cases what happens? The parameters of differential causal elements get associated with other storage elements which have the integral causality. So, in presence of differential causalities, the order of the state equation is smaller than the order of the system because storage elements can depend on each other. Now this kind of dependent storage element each have their own initial value, but they together represent one state variable and their input signals are equal or related by a factor which may not be necessarily constant. So, this is what happens by the differential causality, and these are the references. You can look at our book on intelligent mechatronic system modeling, control and diagnosis for further details of it. Thank you.